Okay, in this video, we are going to look at the construction of DFAs, involving modulo arithmetic notations. So modulo arithmetic notations are very important as far as computer science is concerned. We apply modulo arithmetic notations in many different fields like cryptography. We extensively use modular arithmetic notations in cryptography, and in theory of computation, when we look at DFAs involving modular arithmetic notations, it's good to know what is a modular arithmetic notation, and then be able to design DFAs involving such notations. So let's begin. So now let us look at what exactly is a modulo arithmetic notation. So when we say that x equal to y mod n, and mod n is written within brackets, that's very important. So when you encounter such a notation, it means that if you divide x by n, that means if you divide x by n, then you will get a remainder of, you will be getting a remainder of y. So once again, when you divide x by n, you'll be getting a remainder of y. So this is very important. So then if in such a case we say that x and y are congruent on modulo n. So let's look at some examples, then it will become more clear. So let's look at this. 38 is said to be 3 mod 5. So now we say that 38 and 3 are congruent on mod 5. So it means that if you divide 38 by 5, the remainder that you are getting will be 3. And this is correct also, right? So and remember, 38 is not the only value that when you divide by when you divide by 5 gets you to 3. There are many other values which will get you the same. So so this is not a single value. Okay, there can be multiple other values which also has the same property. For example, instead of 38, I can also say 43. 43 is also can be said as congruent to 43 and 3 are congruent on mod 5, just because upon dividing 43 by 5, you get a remainder of 3. Similarly, look at this example. This example says that 10 and 4 are congruent on modulo 6. It means that if you divide 10 by 6, then you'll get a remainder of 4. You'll get a remainder as 4, and that's correct. So these notations are very important when we look at some of the questions involving these notations. So let's move ahead towards solving such questions. So in this question, we are asked to design a DFA to accept binary strings with number of ones equivalent to 1 mod 3. Okay, so this question can be slightly modified. Suppose if your alphabet set is on A and B, then you can also be asked about number of A's equal to 1 mod 3. So the question can be modified. Okay, now let's try to solve this. So the number of ones, so this notation essentially means that the number of ones, when divided by 3, should always get a remainder of 1. So the number of ones can be 1, it can be 4, it can be it cannot be 5, right? It cannot be 6 also. It can be 7. It can be 10, and so on. So these are the number of ones that is possible in our binary string, and we should accept only those strings having the number of ones equal to 1, 4, 7, 10, etc. in this series. So let's try to solve this. Okay, let's start constructing the DFA. Okay, so let Q0 be our initial state. and from Q0, so we are interested in counting the number of ones. So we want the number of ones to be 1, 4, 7, 10, etc. Okay, so we are actually not worried about the number of zeros as such. Okay, so we can have the transition. If you see a 0, you can come back to Q0. If you are seeing a 1, you can go to Q1, and from Q1, if you see again a 1, you can go to Q2, right? And then if you see a 0 at Q1, you can stay there because we are not interested in counting zeros. Again, if you are seeing a 0 in Q2, you stay there because we are interested in counting the number of ones. And now if you see a 1 from Q2, you can actually come back to Q0 so that it when you come back to Q0, it means that you have seen 3 ones, right? So if you are again at Q1, then it means you have seen 4 ones, right? So in the next rotation, if you again come back to Q1, it means that you have seen 7 ones. Similarly, if this rotation continues, then it means that you have seen 10 ones, right? So it's very easy to understand with CSS. Suppose if you want the number of ones to be divisible by 3, okay? So in that case, it's very easy to see that if you come back to Q0, then it means that the number of ones that you've seen is divisible by 3. That means your remainder is going to be, the remainder upon division by 3 is going to be 0. So such numbers are 0, 3, 6, etc. So if your string terminates in Q0, the state Q0, it means that the number of ones in that string is divisible by 3. But we want a remainder of 1, right? We don't want a remainder of 0. We want a remainder of 1. So it means that when you are at Q0, means that the number of ones is 0. But if you are at Q1, it means that you are seeing the remainder as 1. So Q1 is going to be your final state here. Okay, so if you are at Q1, it definitely means that the remainder is going to be 1. Remainder in the sense the number of ones. Okay, the number of ones when divided by 3 will give you a remainder of 1. So let's look at some examples. Let's say our string is 101110. Okay, so this string contains 4 ones. Let's say how it gets accepted, right? So let's go through this. So our first alphabet is a 1. So upon seeing a 1, we shift from Q0 to Q1, and then we have a 0. We stay at Q1. Then we have a 1. We go to Q2, and then we again have a 1, right? So we come back to Q0, and then again we are seeing a 1. So we will be at Q1. And from there, you're seeing a 1, you're seeing a 0, right? So again, you'll be at Q1, right? So this string gets accepted. We can see that the number of ones here is 4, and this string gets accepted. Let's say, let's look at what happens if one more 1 is there, right? So if this is the string, then from Q1, you have to make a transition on 1. So that means you will be at Q2, right? So when you see one more 1 there, you will be at Q2. It essentially means that you've seen 5. You have seen 5 ones, right? So this is the way that we are going to design this. Okay, in this question, we are asked to find, accept the binary strings whose number of zeros is congruent to 2 mod 4. It means that we have to accept those binary strings whose number of zeros when divided by 4 will give you a remainder of 2. Okay, so such combinations will be, if the number of zeros is going to be 2, it has to be accepted because 2 mod 4 is going to be 2 itself. It can be 6 because 6 mod 4 is going to be 2. It can be after that it can be 10 because 10 mod 4 is going to be 2. 14 mod 4 is also going to be 2, and so on. This is the if your binary strings contain 2, 6, 10, 14, etc. number of zeros, then you are going to accept that. So let's begin. So since we have already designed for the previous question, this is going to be very easy. So let's start at Q0. And so we are going to make a move only upon seeing zeros. So if you see a 0, move to Q1. Again, if you see a 0, move to Q2. Again, if you see a 0, move to Q3. And at Q3, if you again see a 0, you can go back to Q0. You can go back to Q0. And if you see a 1 at any of these states, you are going to stay there, because we are not interested in counting the number of ones. We are only interested in zeros. So at any state, if you see a 1, you have to stay there. Okay, so this is going to be our DFA. So this is going to be our DFA here. Okay, now okay, so that's complete. So okay, one more thing, we have to mark the final state, right? So if the question was about to find those binary strings whose number of zeros is divisible by 4, then Q0 would have been your final state. If it was the question was if you divide the number of zeros by 4 and then you have to get a remainder of 1, then Q1 would have been your final state. But the question is we have to get a remainder of 2, so we have to make Q2 as the final state. So let me double circle this Q2 so that it is represented as a final state. So in this example, this is going to be your final state. Okay, so we can easily generalize this. So for any given values, for example, say number of zeros here is going to be, let's say, R mod n. So this is suppose this is the question given, then what you can do is you can start at Q0. You have to go to Q1, etc., and QR will be your final state, because you want to get a remainder of R here, right? So QR will be your final state, and then you have to continue this. You have to continue this until upon getting zeros, you have to make transitions to the next state. You have to do this until Qn minus 1. And from Qn minus 1, if you see again a 0, you have to get back to Q0. If you see a 0 again here at Qn minus 1, you have to get back to Q0. Okay, and QR is going to be your final state. This is very important. QR is going to be your final state because the remainder that you require is R. And since there are n, mod n is the division that you're doing, you have to have Qn minus 1 states up to here. And from there, if you see a 0, again, you have to go back to Q0. And don't forget to, show the transitions on 1. So from Q0, if you get a 1, stay there. Q1 upon 1, stay there. QR upon 1, stay there. Qn minus 1 upon 1, stay there. So this is the generalization of this. So if you want number of zeros to be R mod, congruent to R mod n, then you start drawing Q0, Q1, and up to Qn minus 1. And QR is going to be your final state. And there are going to be n minus 1 states here. Actually, there are n states, right? There are n states from Q0 to Qn minus 1. So this is the thing that you have to remember. Now we have one more type of questions which may be asked. These are based on the binary values of binary strings. So this is a question which can be given as an example. So binary strings whose integer value is congruent to 0 mod 3. This means that suppose if our binary value is say 110, binary string is say 110, its integer value is going to be 6, and 6 mod, and if you do a modulus operation of 6 with 3, then you will get a remainder of 0. Okay, so 110 has to be accepted by our DFA. So this is the meaning of that. Suppose the binary string is say 101, then the decimal value is going to be 5, and 5 mod 3 is not 0. 5 mod 3 is actually 2. Okay, so it should not be accepted. This should not be accepted, whereas 110 has to be accepted. So let's look at closely. So the minimum strings which has to be accepted, and then we can try to build our DFA. So for making it very easy, I have listed out the binary values, and its equivalent decimals and the remainder that you're getting upon when you divide by 3. For example, if the binary value is just one alphabet, that's 0, then the decimal value is 0 itself, and this remainder, that is 0 mod 3, is going to be 0 itself. So if it is 1, the decimal value is also 1. 1 mod 3 is again 1. So this should not be accepted. This has to be accepted because the remainder is 0. So this has to be accepted, whereas this should not be accepted, right? So this 1, if you see just 1, it should not be accepted. If the binary string is, say, 1 0, it has a decimal value of 2, and the remainder is going to be 2. So it also should not be accepted. So here again you have 1 1. 1 1's decimal value is 3, and its remainder, remainder on dividing it by 3 is going to be 0. So this should be accepted. Similarly, if you look at this should not be accepted. This should not be accepted. 6 has to be accepted, right? So we have to design the DFA for this. So let's begin. So let's say Q0 is going to be our starting state. Okay, so Q0 is our starting state. And from Q0, if you see a 0, okay, so if you see just a 0, it has to be accepted, right? So Q0 is going to be a final state, because upon seeing a 0, so this is the, okay, upon seeing a 0, it means that remainder is also 0 for that binary value. Then Q0 should be an accepting state. And again, if you see a 1, after that, or 1 is the value if you are seeing, then it should not be an accepting state, because 1 is not accepted, right? 1 is not accepted here. And if you see a 0 again from Q1, okay, from Q1, if you see a 0, that means you have seen 1 0, and 1 0 should not be accepted, right? So it should not be an accepting state. And from there, if you see a 1, okay, let's finish the 0 first. If you see a 0, or let's look at what is happening when you're having 1 0 1. So if you're having a 1 0 1, it should not be accepted, right? So it should be at Q2 itself. Okay, because Q2 is not an accepting. I'm not making Q2 as an accepting state. Now we can see that if you're getting 1 0 0, if you're getting just 1 0 0, it should not be accepted. But if you're getting 1 0 0 1, it has to be accepted, because this is the binary string. The equivalent value of this 1 0 0 1 is going to be 9, and 9 has to be accepted. Okay, so to make that happen, from Q2, if I'm getting a 0, I will move to Q1, so that 1 0 0 is not getting accepted. But I have to make I have to make something to do something to I have to make 1 0 0 1 gets accepted. Okay, so if I'm getting a 1 from Q1, I have to go to Q0. Okay, I have to go to Q0 if I'm getting a 1. So I have to also make to accept 0 1 1, because it's 3. So if you're getting a 0, you stay at Q0, and then if you're getting 1 1, then you'll be back at Q0. So this DFA is going to represent the DFA which will accept binary strings whose integer value is congruent to 0 mod 3. Now let us draw its transition table for this particular DFA, so that we will get some interesting observations. So if you draw the transition table for this DFA, I have 3 states, Q0, Q1, and Q2. So let me write the states here. So I have Q0, Q1, and Q2. And I have transitions on 0 and 1. So I have a transition on 0. I also have a transition on 1. So let me fill this quickly. So once we have filled this, we will have a very interesting observation here. So let me use a different color. So Q0 on 0 gets you to Q0 itself. Q0 on 1 gets you to Q1. Q1 on 0 gets you to Q2, and Q1 on 1 gets you to Q0. and Q2 on 1 stays at Q2. Q2 on 1 stays at Q2, and I have to write the 0 transition here. Okay, so Q2 on 0 gets me to Q1, and Q2 on 1 gets me to Q2 itself. Okay, so if you look at this pattern, so you can see that from here, if you look at it, is going like this: Q0, then Q1, or let me use a different color. So from here, if you look here, it's moving like this: Q0, Q1, and then Q2. Okay, Q0, Q1, Q2. Again, the same pattern is getting repeated: Q0, Q1, and Q2. So this is an interesting observation, and this is also valid for similar questions. For example, if the question is to identify binary strings whose integer value is, say, let's say 0 mod 4, the question is like that, then the transition table, very interestingly, the transition table will look something like this. So you will have Q and transitions on 0 and 1 here. Okay, so and you will have Q0, Q1, Q2, and Q3. Because since you have mod 4, you have 4 transitions here, right? So this is going to be something like this. So it will be something like this. So you start at Q0, Q1, Q2, and Q3. Again, repeat the same pattern: Q0, Q1, Q2, and Q3. So this interesting pattern is going to repeat again and again. So this is applicable to all these types of questions. So we will do one more question, and then we'll understand how it can be done. So before moving to the example, let's look at another interesting fact about this DFA. So whenever your binary string ends at Q0, so if you are given a binary string and then you are parsing it through your DFA, and whenever it ends in Q0, it is very interestingly the remainder upon division by 3 is going to be 0. So if your binary string end at Q0, it means that your remainder is going to be 0 upon division by 3. Similarly, if your binary string ends in Q1, okay, so we designed the DFA in such a way that if the binary string ends in Q1, it means that the remainder is going to be 1 upon division by 3. Similarly, if the binary string ends in Q2, okay, so in that case, the remainder is going to be 2. Let's go through some examples and understand that. So let's say our binary string is 1100. This actually refers to the decimal number 12, and we know that 12 is divisible by 3. That is, the remainder is going to be 0. So we expect that this binary string will terminate at Q0. Let's check what is happening. Okay, so when you are encountering 1100, it goes like this: from Q0 you're going to Q1, 1, again 1, coming back to Q0, again 0. So you are at Q0, and that means your remainder is 0. Look at another one. So this is 1101. The decimal value of the same is 13, and the remainder upon division by 3 is going to be 1. So we expect that this binary string will end at Q1. Okay, let's look at what is happening. So from Q0, you're going to trace the string 1101. So okay, from Q0, 1, 1, 0, and again 1. So you are at Q1 finally, right? So we can say that its remainder is going to be 1. Okay, so actually we designed the DFA. We can use this fact while designing the DFA itself. So similarly, look at 1110, which is 14, and its remainder upon division by 3 is 2. So we expect it to end by Q2. let's see what is happening. So from Q0, 1, 1, 1, 0. You can see that it ends at Q2. Let's look at one more thing. It is 1, 1, 1, 1. The binary value, the equivalent decimal value is 15, and 15 is divisible by 3. That means the remainder should be 0. Let's look at what is happening. So 1, 1, 1, and 1. So it's coming back to Q0. So the remainder is going to be 0. So this is a very interesting observation, which can be actually put to use while designing these kinds of DFA. So suppose your question is, instead of 0 mode 3, suppose your question is say a 1 mode 4. Then instead of 3 states, you should have 4 states, because you expect remainders as 0, 1, 2, and 3. You can have 4 remainders when you divide by mode 3, which are, sorry, by if you're taking a mode 4 operation, possibly you can have 4 remainders, which are 0, 1, 2, and 3. So you should have Q0, Q1, Q2, and Q3. And if the question is for 1 mode 3, okay, then you expect that the binary string should end, the final state has to be Q1. Okay, we will look at a few more examples to illustrate the same. So this fact is very useful while designing these types of DFAs. In this question, it is asked about binary strings whose integer value is 0 mode 4. So from the knowledge about the transition table which you have described earlier, we can easily start drawing its transition table without even looking into the question. It's a shortcut method, right? So you have Q, let's say, let me use a different color. Okay, I have the states here. I have the states here. Okay, and then I have the transitions here. 0. This is the 0 transition, and this is the 1 transition. So since it's a question on mode 4, I will have 4 states: Q0, Q1, Q2, and Q3. So these are the 4 states which I'm having. And the only thing you need to do is to follow this sequence, that is Q0, Q1, Q2, Q3. So all the states you have to write in a sequential way. Again, here, continue that pattern: Q0, Q1, Q2, Q3. Okay, so this is going to be our transition table. And from this transition table, it becomes very easy for us to draw the DFA. So one more important observation here is that you can see that there are some, for the transitions, if you look into the transitions on Q0, Q0 on 0 is Q0 itself, Q0 on 1 is Q1 itself. Similarly, Q2 on 0 is Q0 itself, and Q2 on 1 is also Q1. So these are identical here. Similarly, if you look at the transitions on Q1 and Q3, okay, if you look at the transitions on Q1 and Q3, you can see that Q1 on 0 gives you Q2. This is actually 2, right? This is 2. So Q1 on 0 gives you Q2, and Q1 on 1 gives you Q3. Similarly, in a very same way, Q3 on 0 also gives you Q2 and Q3. So if you look at the transitions here for Q1 and Q3, they are also the same transitions here. Also, we have to remember, we have to also make note that Q0 is going to be the final state here, because our remainder that we want to get is 0. So Q0 is going to be our final state, and it's also the starting state. Okay, so now an important rule here is that if you have, for 2 different states, if you have the same transitions, you can actually merge them if they are not, if they don't contain a final state. So if you look at Q0 and Q1, if you look at Q0 and Q2, okay, if you look at Q0 and Q2, they are having the same transitions on 0 and 1, but one of them is a final state, because Q0 is a final state, so they cannot be merged. So the important rule here is that you cannot merge, you can't merge final state, can't merge a state with a final state. Okay, this is important. But look at Q2 and Q3. Q2 and Q3 are normal states. They are non-final states, right? So you can actually it's not sorry it's Q1 and Q3. So look at Q1 and Q3. Okay, Q1 and Q3. So if you see Q1 and Q3, okay, Q1 and Q3, the transitions on 0 and 1 are same. Okay, so Q1 and Q3 are identical states, and none of them is a final state. So I can actually merge Q1 and Q3. I can actually merge. I can do a merge on. I can merge Q1 and Q3 because the transition information is the same. Look at here. Q1 on 0 gives you Q2. Q1 on 1 gives you Q3. Exactly the same here. Q3 on 1, Q3 on 0 gives you Q2 again. Q3 on 1 again gives you Q3. So these states can be merged as a single state. So Q1 and Q3 can be merged as a single state. And I can, instead of having two different rows for that, I can just have one row. Okay, let's see how it can be done. So what I'm doing here is the trivial reduction of a DFA. So you can actually draw the DFA from this transition diagram itself. So if you draw the DFA from this transition diagram itself, you will be having 4 states. Okay, you will be having 4 states. So instead of that, I can reduce it further to 3 states if I merge Q1 and Q3. Look at Q1 and Q3. The transition information on both Q1 and Q3 are exactly the same. So, and none of them is a final state. Q1 is not a final state. Similarly, Q3 is also not a final state. So we can actually merge them so that the number of states in your final DFA reduces to 3. So let's try to draw the new DFA. So it will be looking like this. So you have the states and you have transitions defined here. So Q0, I cannot do anything with Q0 because Q0 is the final state. Right? It's also the starting state. And the informations are Q0, Q1, transition information. And what I'm going to do here is I'm going to merge Q1 and Q3. So I'm going to call it with a different name. Say, let's say Q13. Okay. Just to give an idea that I have merged Q1 and Q3, so I got a new state which is Q13. Okay, so the transitions are like this. So I'm getting upon 0, I'm getting Q2, and look at here. The transition of Q1 on 1 is Q3. Now we have started to call Q1 and Q3 is now called as Q1, Q3. Q13. Okay, so one important thing to remember here is that I don't have Q1 and Q3 anymore. Okay, so I'm not having Q1 and Q1 comma Q3. So I have merged this as Q13. So whenever I see anything, if I see a Q1, I will call now it as Q13 because they are merged. Q3 also is going. I'm going to call this as Q13. Right. So whenever I see Q1 or Q3, I'm going to call it as Q13 because there is no state like Q1 or Q3 now. So whenever you see a Q1 or a Q3 in your old transition table, now I will call this as Q13. Okay. So the naming is not very important. You can call it even A or Q13 can be represented in your DFA using any letter. Let's say A or P or something. So but we want to actually look at we want to actually replace Q1 and Q3 with Q13. So for transition 1 here I have Q3. So I don't have Q3 anymore. So I'll be having Q13 instead. So this is very important. So whenever you see a Q1 or a Q3, you have to call it as Q13 because they are merged. Now for Q2, let's write the transitions from Q2. Q2 I have Q0 on 0 transition, and Q1, again Q1. I don't have a Q1 anymore. Instead of Q1, I will have Q13, Q13. And the next state in the old transition table is Q3. So I don't have a Q3. I have only Q13. So okay. So we have actually merged. You don't have to write this, right? Because we have actually merged 1 and 3, and then we said it is Q13. So that's all. So this is going to be our total information. Okay, so we can see that there's a reduction of states here. So we have, in this diagram, we have only 3 states here. We have only 3 states. So what we have done, let's quickly recap what we have done. We looked at the transitions one by one, and then we have understood that some of the transitions are the same. For example, Q0 and Q2 had the same transitions, but the problem was Q0 was a final state. So we are not able to merge Q0 and Q2. But look at Q1 and Q3. Q1 and Q3 are also having the very same transitions on 0 and 1. And none of them is a final state. So we can easily merge them. And instead of saying Q1 and Q3 separately, we called it as Q13. So whenever we saw a Q1 or a Q3 in any entry, we replaced it with a Q13. So now our new transition table contains only 3 states. And using these 3 states, we can easily draw the DFA. Okay, in the transition table, there is a mistake. You might have noticed it. I have written Q1 here. So we don't have Q1 anymore. It is going to be Q13. Okay, so the important thing that you remember is that whenever you see Q1 or Q3, you have to call it as Q13. Okay, so now we can easily draw the transition table corresponding to this table. And transition diagram corresponding to this table, and it will contain only 3 states. So let's quickly draw the transition diagram, the DFA. Okay, we can draw the diagram for the DFA very easily. Now I have already drawn the states here, which are Q0, Q13, and Q2. So we can see that Q0 is a final state itself. So Q0, I will double circle it. And from Q0 upon 0 goes to Q0 itself. Okay. Q0 on 1 goes to Q13. And let's look at the transitions on Q13 now. Q13 on 0 goes to Q2. Oops, sorry. Q13 on 0 goes to Q2. And Q13 on 1 goes to itself. Okay. And Q2 on 0 goes to Q0, Q2 on 0 goes to Q0, and Q2 on 1 goes to Q1. So this is going to be our DFA. So this DFA contains only 3 states, whereas if we draw the DFA for this transition table, it will contain 4 states. That's why we say that we have done a minimization. So what we have done is called a trivial minimization. So we looked at the transition table. And then we understood that there are some identical state transitions, and then we could minimize it. This is a trivial way of minimizing it. So we will also learn about, in future, we will also learn about DFA minimization. Okay, so DFA minimization, it is not only about the trivial minimization. Okay, so we can actually minimize a given DFA by looking at these kinds of trivial things, and there are more things also that we can do for minimizing a DFA. So we will look at DFA minimization in one of our future videos in depth. But what we have seen in this video is a trivial way of minimizing the DFA from the transition table. Now, as an assignment, you can work out these problems. That is, strings that start with let me take. Okay, the strings that start with an A and the string length is 0 mod 3. So, and the alphabet set here is A, B. Remember that all the questions that we worked on 0, 1 can also be replaced with A, B, where the alphabet set is A, B. Okay, so here the string has to start with A, and the string length has to be 0 mod 3. So since here also you can see the AND closure, but you don't it is not necessary that you apply the intersection operation that we have discussed. So it can be trivially solved. The only thing is that the string should start with A, and then the string length. It's only mentioned about the string length. It can be it is not mentioned that the number of A's or number of B's. It is just mentioned the string length has to be divisible by 3, including the first letter, which has to be an A. Okay, so that's the first question. And the second question is binary strings whose value is congruent to 1 mod 6. Okay, so binary strings whose value when divided by 6 will give you a 1. Okay, similarly, and remember this has to be minimized. So from this question you can understand that if you are drawing the transition diagram and applying that, if you're drawing the transition diagram straight away, you will get 6 states starting from Q0, Q1 up to Q5. You'll have six states, and you have to have Q1 as your final state. That's what it means. So in your transition diagram, it's very easy to draw the transition diagram. We have already shown how we can do it. Okay, with 2 examples. Okay, now your transition diagram will contain the values from states from Q0 to Q5, and your final state is in this case, it's since the remainder has to be 1, the final state is going to be Q1. Okay, so if you draw the transition table and straight away draw the DFA, your DFA will contain 5 states. Okay, so you should always look for minimization. Okay, so you can actually minimize it. Further. So without minimization, you will have 5 states in your answer. It's not 5. It's going to be 6, right? It's going to be 6 states because including Q0, right? So you'll be having, let me say, it will be having 6 states without minimization, right? And if you look for minimization, you have to look for the possibility to merge 2 states. Okay, so while merging, you should make sure that you're not merging any final state. Okay, you should not take final states, consider final states for merging. Okay, so if you do some merging, you can minimize it to 4 states. Okay, so so the most minimized answer is always preferred. So so it should contain 4 states only. And similarly, this question is to accept binary strings. The third question is to accept binary strings whose value is 3 mod 8. And if you do it trivially, you will have 8 states starting from Q0, Q1, etc. up to Q7, right? And Q3 in this example, Q3 is going to be your final state because you want a remainder of 3, right? So if you draw trivially, if you draw the transition table trivially, you will have 8 states, and Q3 will be your final state. Okay, so if you draw trivially, you will have 8 states. And if you look for some minimization, I think minimization is possible in this example, and you can actually come up with the 5 states here. You can actually come up with the 5 states after minimization. So you are always expected to do minimization if that is possible, right? Okay, so these are the guidelines for the assignment. So whenever you submit the assignments, so we have already looked at assignments on complement representations. Complements. We have had assignments on union and intersection. Okay, and now I am also giving an assignment on modulo arithmetic based construction. Modulo arithmetic. So remember that only one assignment is posted in your Moodle with a heading assignment set 2 on DFA construction. So whenever you are doing, submitting this assignment, you have to submit it as a single document, and you have to give headings. Okay, if you are doing a complements problem, you have to give the heading as complement, DFA for complement representation. And similarly, the next set when you're doing, you have to give that heading. If you're doing modulo arithmetic, you have to give that heading, and under that you have to write the solutions, right? So this is going to be a single assignment. It's going to be a single assignment under Moodle, which has got the name assignment set 2 on DFA construction. Okay, assignment set 2 on DFA construction, and you have 3 headings. Okay, so you have to show your solutions under these 3 headings. So if I'm giving some more videos, okay, it will also be getting added to the assignment set 2 on DFA construction. So I forgot to mention one more question that's been asked in your university question. So it's again based on modulo arithmetic notation. So the question is, to find the binary strings with value equal to or value congruent to 1 mod 4. Okay, so these types of questions are very easy once you know the method. So you can actually work out this question also as part of your assignment.